Okay, let's get started. So we're going to talk about blur filter, but before that, let me recap what we talked about last time. So an image is formed by, you have a light source and you have a surface material, like what you see here, and the surface material will reflect light, and those light will be recorded by a camera. Okay, so that's basically how an image was formed. And through the process, last time we talked about you have a surface, you have different types of refraction models, and based on the understanding, you can build application like you take a photo, take an object from different lighting, and you can recover the surface normal. You can do 3D reconstruction by just looking at image pixel values. And toward the end of the lecture, we talk about the imaging system. Specifically, you could also, based on the understanding, you can also build a application like HDR. And so we were a little bit rushed at the end. So let me try to properly explain this one more time. So the idea is that you have you want the image to recover the dynamic range of the light intensity in the scene. But what you observe is that because the camera has a nonlinear function between what you observe and what they recorded, and the camera is only sensitive does not have the sensitivity does not have that wide dynamic range. It only has a specific range, and therefore when you capture a photo, typically outside, you will see either it's too dark or it's too bright. Okay. So what you want is to be able to capture different exposure time of the same scene and be able to recover the full dynamic range. Okay. So how do you do this type of computer vision problems? So you have a pixel value like Z1 for a particular pixel in multiple images. You have Z for eyes exposure. You have ZI1, ZI2, ZI3, ZI4. Okay. And because each exposure has different exposure time. So what you observe here is that your exposure, like amount of light you receive from each image, is the radiance. That's the intensity, the actual intensity from the scene, R1 I, and times the time duration. Basically, you open your shuttle, the light comes in, and you integrate, you multiply this radiance and time, and that will give you the radiance. That will give you the exposure. So you have this simple things. It's the same radiance, it's same R, but get exposed to different time. So some of them will get exposed longer, but they may get overexposed. Some of them exposed shorter. Then you can capture something that's very bright. Okay, and then you have this relationship that is the intensity. The intensity you actually observe in your camera equals to the irradiance, basically the exposure, and plus goes through this function. That's the nonlinear function. Yes. What was that? We won't need to implement this in code, but I think it's good to understand that these type of problems, and you can set up the unknowns and known, and it will be able to solve it with linear equations. That's the point I want to get, that because this pattern will appear many times throughout the course. Basically, you have a problem, you have an observation, you have unknowns. How do you set up a system equation and be able to solve it? So when you do that, you actually, once you understand how you set up a linear system equation, it's very easy to implement this in Python. Yeah. All right. Okay. So there's this simple relationship, right? So you have a function that is the pixel value equals and the camera response function that takes the irradiance times the exposure time. All right, so you want to, last time we talked about, you want to, you can, instead of modeling the camera response function, you can model inverse of that, right? Camera response function basically is an input that's the irradiance over time, and output is the intensity value that the camera actually observes. All right. And then you can take the log so that they compose these two terms, and this will be your relationship. Okay. So last time we talked about basically what you want is to somehow minimize these things and solve for the unknown. Okay. Basically want to say, how can I solve the unknown so that these guys are minimized as minimized as possible? And the objective function involves like summing up over all the images you capture, summing up all the pixels you capture. Okay. So, and then there's a weighting term here I didn't talk about last time. Basically, it's very simple. Basically, it says that if the pixel value intensity is close to 0 or close to 255, that those pixels cannot be trusted. So you have a weighting term that looks like this, right? So if the pixel value is close to the 128, it means that it's well exposed. So those pixels are more trusted. Okay. All right. So, and then you can have some regularization that says that the second order, so this sounds complex, but it's not. So what it says that this camera response curve, the second order of the camera response curve should be minimized. What does that mean? What if I have a function and if I take second order derivative, what does that mean? What am I measuring? The first order, let's say first order. If I take the derivative of a function, what do I measure? Any idea? Suppose I have a function. What does it mean to take the first derivative, the gradient of that function? Yes. Yeah, the change over time. And what's the second derivative trying to do? Yes. The change over time. Yeah, the change over time. So that is how smooth they are, right? How smooth they are. All right. And this term basically says that basically says that I want a smooth function. All right. I want a smooth function. That's a regularization. So what I do know is the time, the exposure time I do have, and what I don't know is the irradiance, how bright a pixel actually is, and the G, that is the camera response. Okay, so how do I do that? Let's reshuffle this so that I have a linear equations. So this is the equation, and whenever I have equations, I have some unknowns, some knowns, right? So what I will need to do is to set this up, and let's first make up some problem. Suppose I have a Z that's only every pixel has 4 different values instead of 256 values. Let's say we only have 4 values, and I only take 3 images. That's 3 exposure, and I have 2 pixels only. All right, so it's very, very simple problem. I have an image with just 2 pixels, and each pixel will take we will take 3 images of this 3 exposure for this image. All right, and each pixel could take on 0, 1, 2, 3 values. All right, so what does it mean? So let's make a problem for pixel 1. In the 3 exposure, I get 0, 1, 2. All right, so this is a darker pixel, and in pixel 2, in the 3 exposure, I get 1, 2, 3. Okay, so this is just a made-up problem. All right, it's very simple, 2 pixels. But what I want to show is that what is the linear system equation looks like. Okay, so here we have the unknown, right? Unknown means that I don't know what the G of 0, G of 1, G of 2, and G of 3 is. This is the intensity to the irradiance function, okay? Inverse camera response function. And also the log R1, log R2. That is the log of the irradiance, the actual intensity, light intensity of that particular pixel. I want to recover the dynamic range. Okay? So when I have a column vector that's full of unknowns, then what I need to do is to set up a linear system of equation so that I can solve it. Right? So this looks like this. it looks like this linear system equations. So suppose I look at the first pixel and the first exposure. This is what it would look like, okay? So you can see that the equation on the top, if you plug in the first pixel and the first equation, you'll find that it's basically G0 minus log R1 equals log delta T1. Okay? So I'm just rewriting that equation as a row of this linear system. Okay? So the first pixel, but the second exposure, it will look like this. Okay, you can see that the second pixel is the intensity is 1. The intensity is 1, so therefore is G1 and it's minus this guy, the log R1 equals this guy. All right. Right, and then you do this for the third exposure, it looks like this. Okay, so now you have G2 minus log R1 equal to this guy. Okay, so you just repeat the same things. The second pixel and the first exposure, you will get this. The second pixel is this guy. So the second pixel at the first exposure, the intensity value you observe in the image is 1. And therefore, you have G1, that's here, G1. So you have 1 here. And now it minus the second pixel intensity value and equals to this guy. All right. So you repeat this process, do the same thing. These are the data terms, right? What you observe and what you observe through this process, and these are the unknown relationship between the unknown and known, right? And this becomes a linear system equation, right? And later on, when I said I need to add regularization terms, what I mean by that is that I want to make sure that this G function is smooth. And what do I mean by smooth is that if I take a middle value times 2 minus the surrounding value, these change should be small as possible. Okay, specifically what I do is the following. You can see that if I take this the center of G2 value minus 2 times minus 2 plus these two, I hope that this should be as close to 0 as possible. Yes.
I don't understand that you made that matrix on the left there. So is it part of it's the pixel values that we observed, and other parts are function and the smoothing functions?
So up to this point, I have only take the observation and the unknown relationship, right? So I take a 2 pixel image over 3 exposure, and these are the exposure numbers I actually observe, right? So you actually take a picture, you have the pixel intensity. So these are the pixel intensity I observe. And from that, you can write down this linear system equation. Okay. So there's another, negative. So we know this expression is true, right? Yeah. Oh, okay. Basically, it's called a second derivative, right? So we talk about the first derivative is just 1 minus 1, and the second derivative is it looks like this: 1 minus 2 plus 1. So basically, it's like you have a function, and you take the center minus 2, add the surrounding. These things should be smooth, should be close to 0. When I have something close to 0, it means that the function is smooth. Right? If you mention that your function is like this, zigzagging, then this term will be large. I don't want to have the camera response curve to be like zigzagging. I want it to be smooth. Okay, and that's basically it. When I say I want it to be smooth, mathematically, it's doing this. Yes.
So what are we trying to solve for in this situation? We're trying to solve for G of value.
Yeah, we were trying to solve a G that basically how the camera respond to light intensity, how to convert irradiance to the pixel intensity. That's G, that's what G is. But at the same time, we also recover what the actual irradiance of the thing is. That's log R1, R2. We're trying to solve for this. Yeah. We're trying to solve for this things. Okay. So for any camera, so this is amazing, right? So for any camera, even though you didn't calibrate that camera beforehand, even though you don't know G or the camera response curve is, you can still solve it. Yes. Yes. Yeah, go ahead.
So the G is the value. Each camera has different curves.
Yeah, different kind of different curve. Yeah. Yes. But of course, if you already know the cameras very well, for example, I have like a cell phone, it's already calibrated. Basically means that I already know what G is. You just don't need that G. You just solve for this, right? So it's become more easier to solve. Okay, does it make sense? Second derivative of that G function, right? So I have G0, like G, you can imagine that it's from 0 to 235. I have a function, right? Mapping between the intensity and the irradiance, okay? And that function should be smooth. And the way we make them smooth is to apply this guy here, okay? Apply this guy here, right? So basically it says that the center point and the surrounding should be, if they add up together, subtract this together, they should be close to 0, right? So think about what the function, what type of function will minimize this guy. It's a straight line, right? The straight line will be perfectly, if you take any point in the middle and subtract to the surrounding, it will be 0, okay? So it's trying to make that function as smooth as possible. The G is a function. The G is a G0, like basically input is from 0 to 255, and it will have its own irradiance. Does it make sense? Okay, so we will encounter this kind of derivative later on in the lectures. Yeah. Yes.
So bottom two rows are the second derivatives of G0.
Yeah. G. Yeah. Yes.
So why is there only like one more row? Why are we not doing second derivative all G0, G1, G2, G3? Why do we not have 4 rows?
Because you encounter boundary conditions right now. So you don't have you don't have G4 and you don't have G-1. So you only need to, if you have 4 numbers, the way I want to make them smooth is that the first 3 numbers, their middle one minus the surrounding one should be close to 0. This one minus the other one should be close to 0. That's why we only need 2 rows.
Assuming the same things apply for the first 6 rows as well as
6 rows.
The first 6 rows.
The first 6 rows is only the data term. Like these guys are it's called regularizations. Basically says that even without any data, I hope to see that this G1 will behave in a certain way, right? Even without any observations. Okay, that's with the concept of second derivative. Basically, I want to make them smooth. Okay. All right. So once you have this, then you can solve this, right? So once you have, and so this is just an anchor term. Basically says that okay, this should be certain value, but that's not that important. But once we have this, basically you can solve least squares problem, and then you will be able to get this guy will be the R1, R2 is going to be your HDR function, HDR image. Okay, so every time you take an HDR outside, it's running this algorithm. It's taking a burst of multiple exposures, and for each pixel, you set up this linear system equation, solve for that linear system equation, then you get the actual radiance. Okay, of course, if you have more HDR bracket, exposure bracket, you get more accurate results. Okay. Questions so far? So I'm not asking you to to really understand like this thing, but the concept that what I want to kind of get exposed to is that the concept of computer vision, you have some unknowns and you have some set up a known set of linear system equation, and you can solve it with the linear algebra. Okay, and this pattern will appear many times throughout the lectures, right? So this is the kind of one of the tool sets you'll use for solving a variety of problems. Okay, so if you are still not that familiar in looking at this type of linear system equation, then it will be a good time to refresh your memory on that. Yes. Radiance is essentially how bright the light source is, and it's kind of, you can think about this the actual energies, the light energies that the light emits from that particular angle to the camera. Okay, and that could be unbounded, right? It could be a very large range. Okay. All right, so we talk about computers. So let's talk a little bit about human eyes. So, and how we perceive color, how we represent colors, right? So human eye is essentially a camera where you have a lens that can bend the light, and so that your light rays coming out from the real world will form an image on top of a firm or CCD sensor. That's the retina. Okay, that's the retina here. And so if you kind of cut through this eyeball and then flatten out the retina, it will look like this. And these are the kind of the RGB things here. They are the cells that are you can think about this as the pixels, right? The pixels of your eye. And can anyone tell me where the light come from? Is it from bottom to the top or top from the bottom? Top from the bottom. Okay, it sounds like this because the sensor is there, but it's actually not. Like, so the sensor is actually light coming from here. Somehow, even all the cells is in front of that, we don't see them, right? So that's kind of the magic that even though we have everything inside it has no effect on that, like ability to affect how we see. Okay, so there are two different types of cells. These are just some facts, like the two different types of cells. One type of cells that is called cone cells. That is called cone cell because they look like a cone, right? They literally look like that. Okay, and some of the cells called rod cell because they look like a rod. Okay, cone cells are responsible for color visions. Cone cells are very sensitive to colors. They have different cones, has different light sensitivity to different wavelengths, and rod cell is mostly on the intensity, like the night visions. Okay, all right. So this is if you kind of cut the eyes and then fraction them out like a different degree, what you find is the different types of cone cell and rod cell density. So at the center, that's the highest resolution of your eye, where you are looking at. That is where you get a lot of cone cells. That's where you see the color visions. Okay, and rod cell is in between. So in the night sky, if you go out and watch a night sky, you will find that the stars, if you look up and find a light star, you often will feel that something is brighter on the periphery, not the center. It's because that your rod cell has more density on the surrounding, on periphery. And that's also where during the night, you don't see the color very well. Like if you get up in the middle of the night, if you don't turn on the light, you'll find that you don't see the color very well. Okay, it's because the color is not sensitive to light. So some facts. One thing that you'll find that, okay, you have a sensor, you have sensor on your cornea, on your retina, but how do you take that sensor information to your brain so that you can process it? So you need a cable, right? Your eye need to have a cable that send the signal to the brain. And this is where the blind spot here, right? So you can see here, this guy, all the density of the cone and rod cells go to 0 because that's where you have a cable that processes this information sent to the brain. Okay, but there's a problem, right? So when you open your eye, you don't see a hole in your visual field. Questions? Yeah. So why don't we see that, right? And this is where the blind spot is. Okay, so here is a test. Okay, so you can see where the blind spot is. Let's first, if you close your left eye and use your right eye, look at the top right corner, and what you will find is that for some time the cat will disappear. Right? Did you see that? I don't know whether it's going too far. Yeah.
I think it's if you look at the cat, then the right dot. If you close your left eye, it's not enough. Yeah.
Okay. Yeah, maybe I forgot which eye is this. Maybe if you open, maybe you close your right eye and use a left eye, and can you look at the dots? The cat should disappear. Okay. Okay, and that is where your blind spot is. Okay, so your visual field actually have a hole in your surrounding. It's just that your brain is feeling hallucinating this concept. And one thing is that if you look at this dot, if you try to look at this dot, tell me what you see from this line. If you look at this dot, okay, close your right eye and look at this dot. Do you see anything happening here? Just connect it, right? So your brain is actually fooling you, right? Your brain is actually filling up this missing information. It's just hallucinate something that makes sense to you, even though you don't see that. Okay, and this is a blind spot, right? So this is where the cable of your eye that process this information. Yes. I don't know exactly, but you can think about the reason why they have this kind of difference. It says that the evolution developed that if you only have the home cell, if you only are sensitive to color vision, then you will not survive very well because you need some sensitivity. That's why you have this kind of dual system, right? So you have some home cell that you can discover, you can see the color very well, so that you don't eat maybe poison food or something. But at the same time, you also have raw cell and then they're distributed in different ways. So to optimize, that's kind of evolution. Okay, so so that's about eyes. So how do we perceive colors? So color, you can think about light is basically electromagnetic energy, and they have a specific wavelength of that. And the way we perceive light is that we have 3 different types of cones. So think about them as RGB kind of cells that are sensitive to different light. So this is the response curve for different sensitivity. So you have the long wavelength, the cell that both sensitive to long wavelengths, middle wavelengths, and short wavelengths. So this L and S. All right, but how do we actually see the color? So early days, people saw that they try to do experiments on see if I can do the color matching experiments. basically what I want to do is that I want to be able to show, like, use three colors, so that I can reproduce all the possible single wavelength light, right? Basically, different light waves have from red to green to blue, different light wavelengths. I want to be able to use three fixed wavelengths light, like these wavelengths, particular RGB lights, to generate light that looks like a single wavelength light. So what it does is a color matching experiment. That is, I have a fixed lamp that I can tune the wavelengths, and on the other side, I have a different power, different combination of color lights, but those wavelengths are the same, are fixed. And the reason why I want to do this experiment is that I want to be able to come up with a display, right? I want to be able to use different lights, and a different combination of these lights, I want to generate different types of color. Okay, that's the purpose of trying to do this. And then you have an observer that's looking at, so basically the setup looks like this. So you have a kind of a barrier, and then you look at this, and then you ask the observer, like these lights, three lights here, and this one light here. You want the observer to see if these two lights are the same. Okay, that's the experiments. And then you can record what are the combination of these three lights so that it give you this single wavelength light. So this is the coefficients you get, right? So that's the coefficient you get. So on the x-axis, these are the test light. You have different wavelengths, the different test lights. And then, so on the y-axis is the proportion, the strength of the different light of RGB light. So ideally, what you want is that you want to take these three lights and a different combination of these three lights. I want to reproduce all the visible light wave spectrum. Okay? All right, but something's wrong in this graph. Can anyone tell me what went wrong? What's wrong? Yes. Yeah, right deep down, right? So there's really what does it mean to have a negative light, right? This doesn't make sense. Okay, so what does it mean? What it shows here is the following. So they found that for some color, that's reason that these colors, what they need to do is that they need to move the red light to the other side, so that they add this up, and then these two should match. They will match. Okay, they need to do this to do this to find the matching color. But this is a very inconvenient, right? We don't like negative numbers. So what we want to do is that instead of using this RGB, let's come up with another coordinate system so that all the possible single wavelength lights will be able to represent it by a positive numbers. Okay, and this is the concept of CIE XYZ. Okay, so what we do is that you take the RGB and you do some linear combination of that, so that now everyone is happy, right? And now every single wavelength light, for every single wavelength, you'll be able to find a combination of X, Y, Z light. Okay? All right. So let's try to understand, based on this X, Y, Z coordinates, we will be able to understand why is there a negative light earlier. Okay? So one way to explain this is the following. So if we look at this XYZ space, and if you kind of cut off this XYZ and cut off this particular spectrum, you get something called a chromaticity diagram, right? And this way you will visualize all the possible light waves. Okay? Okay? And then this is all the visible light we can see. Okay, these are all the possible range of colors we can see. Okay, and there's like earlier when we showed that we want to change the wavelength, that's a single wavelength, this is the line we are trying to probe here, okay? So there are several benefits of representing color in this way. The first one is that you can specify what the white color is, right? White color basically is like a equal intensity for X, Y, and Z. That's this guy. And then you can also specify the device environment color. Okay, for example, this guy, everyone, no matter what the device is, as long as it specifies X equal to 0.1, Y equal to 0.3, it's the same universally. Okay, so this means that, for example, if I have a traffic light, like universally every place on Earth, the traffic light is that light. Okay, it's device invariant. So I don't need to, when I communicate with other people earlier, I don't need to, I can be specific. These are not this color is not depending on subjective things. It's based on the physics. Okay. So you can also use this to describe color mixing behavior. Suppose I have one light here, R and G, and you can see that the middle ground is yellow. Okay. If R and B, the middle ground is magenta, and R and G, this is cyan. Okay. So because this is how you kind of mix light. All right. And then you can also explain the complementary color. For example, if you have a blue color here, you have the complementary color means that it's go all the way to the other end, then you get yellow. Okay. So the early experiments we showed earlier that if you have three source of color, different wavelengths. So what you do is that you want to explain all the colors from the spectrum. But the problem here is that for these colors, what happened here, right? Like for this color, you cannot really explain this, right? Because it's outside of this triangle. And therefore, you have to move this back to this, right? You have to move this back. You have to add some negative red color in order to represent this. So this is why you have the negative colors. Okay. All right. So once you have this, you are able to kind of come up with the main problem of this color space is that it's not uniformly distributed. So you can see that the red, so you can see that the greenish color, they have occupy more space. And therefore, you can do some kind of nonlinear transformation to come up with something that's uniformly, perceptually uniform. And this is where the CI LAB space looks like. It's very complex, but what it says is that the Euclidean distance between two colors will be the same no matter where the color is. Okay, so they come up with the space so that you can, when you say that these two colors are different in 5 units, it doesn't matter these two colors are red or green or so on. Okay, because they come up with this perceptual uniform color spaces. Okay, yes. Yeah, so you have 3 numbers for one color, describe one color, and 3 numbers for describe another color. Let's say the utility distance between them is 5, right? So how different they are does not depend on which color it is. Okay, so this is useful because when you do the computation to describe color difference, then you will want to use, whenever you want to describe the color difference, use CI or IB space will be more convenient. All right, so there are many other color spaces that people use. RGB is very easy to use because that directly specify how the device every device will have different RGB light, and then how much they emit light to mix this light, to mix whatever colors. Okay. Just a side note that if you go out and buy display, sometimes you'll find this diagram here in the back of the display. And because display manufacturer, they will want to make sure that you can make this triangle as big as possible. Okay, because if you can make them as big as possible, your display will be able to display will reproduce color that are more vivid, that represent more diverse color. Okay, so this is one of the kind of major kind of design choices. Yes.
So with CIE was just like the how humans perceive color and art is kind of like how computers.
Yeah, how computers generate these things.
So CIE RGB has like a combination of both, like how I guess computers and humans do the same range of color and stuff.
So CIE color spaces is designed for color reproductions. How can I reproduce certain color? And so from the fixed set of single wavelength light. Yeah, so these are single wavelength lights. You can see that the single wavelength is leads on this boundary. How can I design single wavelength light so that I can reproduce this? So it's for, I want to design a monitor. So in order to design a monitor, I want to generate lights, single wavelength light that can reproduce, that the combination of them will be able to reproduce more color. But the problem of that is that from the color matching experiment, we find that you will need to do this negative things. And therefore, we need a better picture to see this color mixing effect. And that's where the XYZ is coming up. Okay, so some other, so this RGB, if you work in the Photoshop or something, HSV is very common. That is basically represent the color in terms of the hue, like what color it is, and saturation, how saturated that color is, and the value is the brightness of the color. Okay, so yeah, so this is just a different color spaces that people can choose from. HSV is very useful for photo editing, for example. If you directly asked you to change the RGB value, it's probably difficult for you to figure out how do I change the RGB value so that I get a specific color. But HSV is very easy. You just have you can change from red to green or to blue very easily by changing these things. All right. So color spaces we talk about, it's basically you have this is a more perceptual uniform numbers. Every pixel is still represented by 3 numbers. Okay, so let's see. So there are different color spaces here, right? So the usage of this how you represent the image depends on your applications. Okay. All right. So what we have right now is that it's very difficult to tell anything from a picture, right? If I see a picture, like you can see that even though different, you don't know really whether this is this pixel is a darker area but face to the light more, or a bright area that's in the shadow. These two colors are basically the same. How do you if you only look at a pixel, because a pixel intensity is determined by so many different factors, depending on the light source, depending on the surface refraction, depending on how the device records the light, right? And therefore, we cannot really understand an image by just looking at a single pixel, okay? And so where is that understanding come from? Okay, when we look at an image, we have no trouble dealing with this, and this is where the filtering comes in, right? So that's why we'll spend a lot of time in the first module only talk about filtering. And filtering essentially is that we want to extract information from local processing, from a local window or into some processing, and there's some mathematical model for doing that. Okay. All right. So the simplest local processing idea is the blurring. Okay. First of all, they have several applications. So for example, if I have a video that's blurred, I have noisy video, I can blur it so that I can remove the noise. Okay. If I have a video that I want to extract structure from that, maybe I want to extract the edges from this, what I will do is to extract the edges. I first need to blur it and extract different scale of the edges. Okay, so this is several different applications of blurring. It's a fundamental operation in many different applications. For example, if you have a cell phone that you can take a photos, and they automatically, because many of the cell phone have stereo. So what they will do is that they estimate the depths, and based on the depths, they will be able to recover, like they blur the background. Okay, they will be able to blur the background like this. Okay, so this synthetically generate the focus blur. All right, so there are several different applications for image blurring. Okay, so what we're going to do is to talk about blurring operations. And we specifically this lecture, we probably will only talk about the spatial operation. How does it work spatially? But that doesn't explain a lot of things. And therefore, next lecture, we will talk about how we can understand the blurring operation, or in general, filtering operations in the frequency domain. Okay? So that's what we are going to do. So let's first of all, if you have an image like this, you typically can describe this image as a 3-channel image, right? Any color image is 3 channels, RGB. This is basically specify how each pixel, the device will send how much light. And then combine them, you see a color image. Okay? So if you look at a local window, what you see is a bunch of numbers. These are the intensity numbers. They are represented in terms of 8 bits. So it's a value between 0 to 235. Okay? So these are the colors. How we represent a color image. All right. Now let's look at the kind of the simple example where I just look at the small resolutions. Okay. So now let's see. Suppose I have this, and this is the input image, and let's visualize the intensity here. The intensity here, like this. Okay. So how can I make the blur version of this? So the simple way to do this is that I have a local window that's called a kernel. This is some name, but it's called kernel. What it does is that it will take pixel values and then take the multiply by these values, 1 in this case, and then add them all together, divided by 9. So what it does is to go compute a local average of every location in the image. Okay, and this operation is called filtering. Okay, so here's what it looks like. You will take this local patch, take these values, and compute the average of this guy, and then you move these pixels to there. Okay, so you move on to the next location, compute this patch, and so on. So you just repeat this process so that you fill up all the blur image. Okay, so the input and output, and this shows the operations of doing this filtering process. Yes. No. Yes. Kernel size, it could be any size. It could be here I'm showing 3 by 3, but it could be like 5 by 5, 7 by 7. But usually they will want to be odd numbers. Otherwise, you will have shift. Yes.
What if you're doing kernel size like 9?
We'll talk about that later on. Like how do you deal with the boundary condition? Yeah. We'll talk about that later on. Yes.
Okay. And so when the kernel moves down, it doesn't use the output in this case. So
yeah, you will not use the output image, right? So it's basically only look at input and process this and then fill in the numbers. Okay. By the way, so this sounds simple, but But if you think about this later on, when we talk about learning, if you just treat, instead of designing the kernel, you can learn this kernel for some processing, and if you stack them multiple together, that becomes convolutional neural network. Okay, so all the advanced object detection systems out there depends on this design, the simple linear functions. Okay, so it's very slow, so let me accelerate this a little bit. Okay, so you can see that once you've done everything, then you get a blur image. It looks like this. Okay, so initially they have some details, and after that you merge all the details. Okay. So now what you see, okay, if you can another question is that you can change the blur size, right? So if your blur size is larger, what the effect is that you'll get more and more blur image, right? So you see that if you're larger, because you average over larger area of pixel values, so you get a lot more blurry results. Okay, so how do you deal with boundary? When I deal with this, when I have this location, as you can see that when I have a blur kernel overlay on the image, it seems that the only valid pixels that are the output image will get smaller, right? That's only the valid regions. But if I want to evaluate the kernel at this location, there are several options. There's no really good options here because we really don't have observation outside. So what you can do is only to approximate this, right? So the common approximation is this. Okay, let's just assume that the pixel intensity just extend, right? Extend this over infinitely, so that you get something that's reasonable. That's one way to do this. Another way is to do the reflections. Assume that the thing is periodic. So that's also a good approximation for some applications. You can also do that. Or you can do other approximations. So that's how you can get handle the boundary. Does that answer your questions? Okay. So this is very simple things, but the problem here is but there are several problems. For example, if I have an input image like this, and if I use this box kernel, that is basically a kernel and with all ones divided by the number of pixels, you will see that the box kernel doesn't really do a good job on blurring, right? This doesn't ideally I want them to be very smooth out, but it doesn't really do the job. Okay, so something is wrong. So instead of this box kernel, so one way to visualize this box kernel is that it looks like this, right? It looks like a flat plan, and then you have a local window that has specific height. That's the weight of the kernel, right? So this is a three-dimensional way to look at this kernel. So one way to to make this is that let's try to smooth it out because it's the upright functions. So maybe we can have some kind of mathematical way to describe a kernel that's more smooth. And one way to do this is to use Gaussian kernel, right? Use Gaussian kernel, it looks like this. So now you have a smooth change, okay? The center is still the largest weight. You still do averaging across the local window, but now your averaging is depending on distance to the center. So the center pixel average more, surrounding pixel average less. Okay. All right. So what is the benefit of this? Oh, right. See. Okay. So if you look at this input image, and now this is visualize the kernel, the Gaussian kernel, and output, right? So if I have a Gaussian kernel and I increase the size of the kernel, basically the sigma of the Gaussian function, you get more and more blur image. Okay. So the question here really is like why both are blurring. Why do we see kind of artifacts like it's not really blurring out all the details in the box blur, but it does a better job at the Gaussian blur. Okay, so this is the mystery, right? So we don't know why, like even though it's just doing some kind of blurring, like weighted average, but why particularly Gaussian blur will perform better at removing high frequency details in the input image. Okay, so in order to understand this, what we really need to do is to understand this from understand the relationship between the convolution and the Fourier transform. Okay, so we want to understand the connection between them. Yes. So high frequency detail means that you have your image. Well, you can think about the image as a function, right? Function is the xy location intensity. Okay, so it's a function so that you have some high frequency that's fast accelerating content and some smooth content. Okay, and any signal can be decomposed into the high frequency component and low frequency component. And the blurring operation is trying to remove those high frequency components. Okay, this will be very important later on. So yeah. Okay, so we want to understand what conversion. So now I'm throwing some jargon, right? So what a conversion is, what Fourier transform is. So some of you may have some experience before, but let me try to kind of reintroduce these concepts and how is it related to operations. Okay, so the main idea is that I have an image, I have an input image, and in any of these kind of filtering operation, let's call it a system. Okay, I have a signal and I have a system that processes that signal from one input signal to output signal. That's basically input output, and the operation we're doing with the signal is called a system. Okay, so it's a little bit complex to explain this in the image. So let's go through. Just think about the image and only look at a scan line. So let's look at a 1D signal. Okay, 1D signal like this. So on the left-hand side, you have a signal that is just 1D, like every pixel location, you have certain intensity. All right, and because they are discrete, so they are basically discrete numbers. All right, so this is the input, and this is the output. Okay, this output is a transformation of the input. Right, so input system process the input, give you the output. Okay. All right, so and this is the T is the transformations. So one particular type of transformation we really like that allows us to characterize the system very easily and has a lot of nice property is called linear and shift invariant system. Okay, so what does that system look like? That system, but a particular set of system is that if I scale up the inputs, and the output, I can perfectly predict what output will look like, because the output is just the unscaled versions of the input, this T of X, and scaled by the A. So a visualization is very easy. It basically say that if you move the input, the output will be scaled the same. Okay, that's called linearity. Also, it means that if I have two signals added up together, apply the transformation, it's the same as the signal apply the transformation separately. Okay, so later on we'll use this process. Okay, so it means the following. So if I have two signals, process them separately. If I have two signals, decompose this into two subsignals, process them separately, and then this will add up together. That's linearity. Okay. So if I have this process, it's called linearity. And there's another one that is called shift invariance. So what does shift invariance mean is that if I have a signal, that's f of x, give you the g, and if I change the position of shift the signal of f of x minus k, the output is the same signal but shifted. Okay, that means that if I shift the input signal, the output will shift correspondingly. So visually, this looks like this. Yes. Work backward. So if I shift, basically it's only one way, right? So if I take an input signal, process, I get an output. If I shift the input signal to the 3 pixels to the right, the output, I can perfectly predict the output. It's the same input, the same output from the unshift version, but shifted to the right. Okay? So why do I have to learn this? Right? So why do I have to learn this? The reason is that later on we will show that this has a big connections. Okay? So by characterizing this particular type of system, this system can be completely characterized by a convolution. Okay, why is that? So remember that the two property, linearity and shift invariance. So let's first decompose this signal. Any signal can be decomposed into something like this. Okay, any signal can be decomposed collection of impulse signal, right? Is this explainable? Like any signal can be said that, okay, how much I have at the 0, how much I have at 2, how much I have at 3, and how much I have at 4. Any signal can be represented this way, okay? And you can then, for every impulses, you pass through the system, okay? You get some response, right? This response looks like this. Okay. So now I have and from the linearity, basically it says that all this the output, you can perfectly predict the outputs by averaging the intermediate one, the collection one, right? So that's linearity. Okay. Right? So you have to compose this one, you can add them up into this one, all right? So let's kind of try to understand this. So you have this signal that this guy is basically doing what we just did, right? Take a signal, decompose into a kind of spike at different locations, right? Spike at different location at different k, shift a bit by different k, and multiply by the scale of that signal. It's basically a kind of trivial representation of the signal. Okay. All right. But what's interesting here is that because scale k is not it's just a scaling because I'm taking this function x. I'm taking this function x, and this part, because of the linearity of this function t, I can move this function inside. All right. This is just a linearity property. Okay. All right. So this is cool. But now, what is this? This function t. Oh, sorry. This function t is operate on this shifted version. So, and this is where the shift invariance comes in, because I have this function. I have this function apply on the shifted version. Okay. What it means is that it's the same as this shifting one. Okay, it's the same of the output from this shifted function, all right, and then shift it. All right. So what is this all about? What it means is that if I have a function, I have a system that is shift invariant, so that's linear shift invariant. What it means is that as long as I know what happened to this system if I sending an impulse signal, and I give you an impulse signal, and I know what the edge is, like the output of the impulse signal. I will be able to predict the output of any signal. Does it make sense? It's very impressive, right? I only need to know what the edge. This basically, I only know if I send an impulse, like locate at 0, what happened to this what's output of the system, and I will be able to predict whatever input, given whatever input, I will be able to predict what the output is. Okay, basically by just taking the signal, shift it, and then multiply this. So this is known as convolution. And you can think about the convolution and the filtering basically the same thing with the flip kernel. Okay, it's basically doing at a different location, doing weighted average, and then give it the output. Okay. So this is another way to look at this. Basically, for every location, you look at different shifted regions, and then you get a weighted average, you get an output signal. For every location, you look at the weighted average, you get an output signal. Okay. All right, so this is where the relationship between the filtering and convolutions. So now with this convolution, we will be able to do something. Okay, so with this, it basically says input and it's Gaussian blur. And what it says is that this can be described by a filter response. And the filter response itself is the Gaussian kernel, right? Yes. Yeah, this only happens when the system is linear and shifting invariance. For this particular type of system, if I know what happened, if I'm sending a impulse signal and observe what happened, and that's your edge, then whatever signal I have, I will be able to predict what the output is. And the reason why is that any signal you have, you can decompose into a bunch of impulses, right? And from the linearity, you know that these are just the output, the combination of all these. Okay, yes. Yeah, you need two properties to make this work. Some system is only linear, some system is only shift invariant, it's not working. So you will need to know more about the system in order to do these predictions. Okay. Let's see. Okay, so I probably will stop here because later on we'll be talking about the frequency domain, where I will need to explain the connection between the convolution and the Fourier transform, the frequency domain, so that I can understand why the Gaussian blur is actually working better, why it works better than the box filter. Okay, let's stop here, and I will continue next time.